Hello everyone, welcome. This is a ECE341 class, the probability and stochastic process. And this class is for the Monday of the fifth week. And we will have the midterm exam on the sixth week. That means next week on Monday we will have the first midterm exam. And this Friday we will have a review. Then next Monday will be the midterm exam. In the exam, I will give you the problems. I post the problems in the Blackboard, and I will also send the problems to you via email. And then you will have like 1 hour to finish your problems, and then after you finish, you need to upload your answer to the Blackboard. You will find there's an assignment where you can submit your papers. You need to scan your paper in computer and make it to be a PDF file. If you cannot make a PDF file, you submit image file is also fine, but I prefer you use a PDF file. Yeah. Then the midterm should be individually, so everyone need to work by yourself and submit your paper. Right? Everyone needs to submit a paper. Yeah. This is not the group work. This is the individual work. All right. And of course, it is a open book, open notes, open tables, open. You can use anything for your exam. All right. Yeah. But the time is limited. I gave you just during the class time. Just during our class time, like 1 hour. We have 1 hour, and after the 1 hour, you will have another 30 minutes for prepare your papers into the style you can upload to Blackboard. So totally you have 1 hour and 30 minutes. All right. So this is for the next Monday, the midterm exam, the first midterm exam. We will have 2 midterm exams. All right. Okay, let's go to today's work. Today we will consider the random variables. Okay. Yeah. The ECE341, the 5th week, Monday class, we will consider the random variables. I use an example to explain it. So we have a coin. You consider a coin. Yeah. You flip a coin, then you can have result. The sample space will be one is the face, one is the tail. So you see the result. They are not numbers. Right? There are some face or tail, some facts. But when you try to write them in in a function way, you need variables. So we can define like this. Use x. Face according to like 1, and the tail according to 0. The x is random. The x is a random variable. Okay? Random variable, and this random variable, its value will be a number. Belong to, I write this way, belong to from negative to positive infinity. And the probability x equal to 1 equal to the probability of x equal to 0, each are half, and the probability of x for any other data, not 1 is not equal to 0. This is 0. Yeah. So this is random variable. Its value could be any number, but only these two values you have a probability, a positive probability, and all the others probability is 0. Right? So things like that. We define x by this way. We have a random variable. Yeah, we can consider another example. I have two dice. Then I threw both. Then I have two numbers, right? So I have a sample space equal to I and j. Both I and j were equal to 1, 2, 3, 4, 5, and 6. So in this case, the sample space, it contains some pair of elements, and we define x equal to I plus j. Okay, now x is also random variable. X is random variable. Random variable, its value, yeah, I write it belong to negative to positive infinite, and the probability. Okay, you need to calculate, but I just write this way. For x equal to k is not 0 if k equal to 2, 3, 4 until 12, right? You need summation of these two. So the smallest value is 1 plus 1 is 2, and largest value is 6 plus 6 is 12. So if k is a value between 2 to 6, this one you have a non-zero probability, and probability of x do not equal to k for any k run from 2, 3 to 12, this one, it is 0. Okay. So we have this. So by this way we have we have a random variable. The probability for this one, you can do a calculate if you want, like yeah, we can list the probability if you want no more details. As for the definition, how to define the random variable, that's enough. If you want to know the probability, now is I write x value equal to k, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Right, this is x. Then the probability for 2. So I plus j is 2. The only possible is 1 plus 1, right? 1 plus 1. So here just one value in the sample space, one sample. The probability will be 1 over 36. Yeah, we suppose this is a fair one. Two fair dice, right? Fair dice. And 3 is 1 plus 2 or 2 plus 1. So I have 2 of 36. And 4, okay, I can have 1 plus 3 is 4. 2 plus 2 is 4. And 3 plus 1 is also 4. So we have 3 choice, right? 3 possible. So this is 3 over 36. And so on. 3, this is 4 over 36, 5 over 36, 6 over 36. Right, this is a 1 plus 6. 1 plus 6, 2 plus 5, 3 plus 4, and 4 plus 3, 5 plus 2, 6 plus 1 is 7. Now 8, which case we can have 8. Now 6 plus 2 is 8. You cannot have 1. 1 doesn't work, right? 1 plus anything, you cannot have 8. So you want summation is 8. So 1 is 2, 1 is 6, then 3 and 5, 4 4. Both are 4. Then reverse. So you have 1, 2, 3, 4. Now you have 5. 5 over 36. Got it. And for 9, which case you can have summation 9. You need 6 plus 3. Then 5 plus 4. And reverse. Right? 5 plus 4 or 4 plus 5. 3 plus 6 or 6 plus 3. So we have 4 over 36. And similar, this will be 3 over 6, 2 over 6, 36. And 12 is just a 6 plus 6, so it's 1 over 36. So you can, the probability can look like this. And all the other equal to 0. This one equal to 0 for any other x, right? For any other x. So we have this one, right? Yeah. And we have another example. We suppose you can you have like a text file. You have a text file in the document in the computer. You have document file, and then you pick any letter from the file. You will have some letter. Suppose we only have letters from A to Z. Doesn't matter, just any letter. Then that letter give us a number. We know that is a ASCII letter, right? ASCII letter code. Like A, according to I can remember this. This will be 101 in A static, right? Yeah, and B will be next one, and so on. So by this way, this is also a random variable. If you want, you can define this is just ASC. Okay, this is ASC. You just see this ASC. So ASC, this one, you use this as a name of the variable, right? Use a name. You can use one letter. You can also use some letters. Right? So I use this as a name of the variable. This one is also a random variable. Get it? Yeah. As for the probability, this depending on the, depending on where you get these letters. Suppose you have a text file, then you use different file, then the letter, which letter will occur how many times, that will be different, right? The probability will be different. You pick any letter from the file, the result, the possibility will be different. Yeah. So here I just give you define the random variable. So this is random variable, right? This is random variable. All right. Yeah. So the meaning is quite simple. You just try to describe everything by numbers. Yeah, this one, if you want to write as a normal number, not in A static, this will be 1 times, this is a squared plus 1, right? 1, then 8 squared, right? So this will be 64 plus 1, 65. Yeah, this one will be 66. Right? This is in 10-edic. And we can know Z, capital Z will be 65 plus 26, right? We have 26 letters. But A already used, so we need plus 25, so this is 90 in 10-edic. Yeah. Okay, so this is kind of random variables. You can check the textbook. They have a whole statement about what is a random variable. The meaning is like a random variable gives a way to assign values to the samples, and events of a random experiment. Yeah, I can have another example. We consider tomorrow's temperature. Okay, tomorrow's temperature. Then that is a T. There will be value. I don't know what it is. It will be something like, I suppose it will be most likely it will be, I use the highest temperature. Okay, because the whole day the different temperature will be different. With the highest one, most possibly it is between 65 to 85. Will be? Yeah, there will be no problem, right? This one. So this is you can consider this is random variable. Random variable. The probability inside this interval, you have probability, and the temperature outside, T equal to a value outside this interval, somehow it is impossible. It is their value, but the probability to get this value is 0. So probability of T do not belong to this one. This is 0. Yeah, you have this. And inside, okay, I just like this. T belong to 65 to 85. I put the whole interval. The whole interval, that is 100%. Oh, maybe I write this for more guarantee. All right. Yeah. So like this. All right. Outside is impossible. And the inside will be some value. And then we can also define x by this way. T larger than 80, x equal to 1, and x equal to 0 for T smaller than or equal to 80. I can define another x in this way. Alright. Then x is also a random variable. Also a random variable. Right? Also a random variable. But of course this is an event. This is not a single value. This is also an event. Right? Actually here, when we define this x, every x according to like this x equal to 2 related to one event, right? One sample. Right? The sample space is this one. I have 2 dice. This is sample space. This is sample space S. And here this x equal to 2 according to one sample. X equal to 3 according to samples in S. That is the event, right? And x equal to 4 also related with 3 samples S. That is the event. So the x give this way. The x give us more more flexible, right? You can use your different way to define this x, and this x according to maybe some samples or maybe some events in the experiment. Right? But one sample is sample, or 2 samples actually, that means event. Right? And here in this sample, this x equal to 1, actually it is related with the event, and equal to 0 is also an event. So here the value of x always related with events here. And here this one T, the random variable T, it is always related with sample, right? Its value, it's just a single value. Right? Yeah. And this one x equal to 1 related with lot of value of T, and T equal to 0, it is also related with lot of value of T. Okay, and alright, so this is the definition of random variable. Then we can have a way to describe the probability in a function way. So we have two functions. Let's say the functions to describe the probability of a random variable. I write into a random variable. That means a random variable. The first function we call the probability mass function. Probability mass function. And for shorter, we can write it as PMF. Probability mass function. It's just like this. Is a p x of random variable x. Right. This function of this x we write as p capital X here of like x. Its value will be probability of x equal to x. And the b we call this is a cumulated probability function. This is a CDF. I lost the part of the number, part of the name. It is a cumulative probability distribution function. Yeah, there's a distribution. Sorry, distribution. It's a distribution of the probability. It's a cumulative distribution, CDF. Right? Cumulative probability distribution. This is probability mass. This is probability. It's a distribution, a cumulative distribution function, CDF, of that same as a random variable x. That is a f x of x equal to the probability of x smaller than x. So we have two functions. Okay, we go back to the example. I use a coin. Then the sample space is face and a tail, and the probability. Suppose it is a fair coin. Then we have probability. I get a face and a tail. They are same. Okay. Now x equal to 1 if we have face. Right? You do the experiment, you will have a result. If you have face, it is 1, and x equal to 0 if we have tail. Then x is random variable. The x is random variable, right? Random variable. And the mass function, the PMF, px of x will equal to the probability of x equal to x. So this value will be 1/2 if x is 0 or 1, right? 0 according to tail and 1 according to face. The probability is 1/2, and 0 for all the others. Otherwise, so we have a mass function. Mass function is this one. You can have a graph to represent, to give sense. This is x. When x is 0, it is half. When it is 1, it is half. So this is 1 half. This is 1. Like this. Alright. So this is a mass function. And then the cumulative distribution function. This is f(x) of x. By definition, this is the probability of x smaller than or equal to x. So what is this? You think it will be 0 if x smaller than 0, right? Because x, only when x equal to 0 and 1, it is possible. Each is a half percentage possibility. When the lowercase x is a negative value, and x is even smaller than this x, then we say it's impossible, right? X cannot be 0 and 1. Okay, if x is if 0 smaller than x, smaller than 1, now the x's value between 0 and 1 include 0. Then what will be capital X? Now capital X will contain the value 0. You have a chance x equal to 0, and which has a probability 1/2. Right? And if x is larger than or equal to 1, then this case contain both 0 and 1. So actually it's 0 plus 1. It is both case, right? It's 1. Make sense? Yeah. No x can be here. Right? You do the experiment. You will have 0 or 1. So you cannot have x. The result cannot smaller than this smaller x. Right? This is negative value. Your result will never smaller than this negative value. And this one, if x equal to 0, it happens. Right? So this is kind of an event. If you get x, capital X is 0, then this one happen. This one happen. Right? Capital X is 0, then 0 is smaller than this x, because x is the value between 0 and 1. And this always happen. Right? Always happen. If capital X is 0, of course 0 is smaller than this x, smaller than the lowercase x. If capital X is 1, now of course it's also smaller than this lowercase x. Right? So no matter capital X is 0 or 1, it always happens. So it looks like this. Got it? And we can have a graph. Now we have 3 values. 0. When x is a negative value, is 0. So it's here. When x equal to 0, but smaller than 1, here is a 1/2. Right? And when x is larger than or equal to 1, this is 1. This is 1. And here is also 1. Alright, so we have this. So yeah, we have two functions. Right? Two functions. And we can consider another example. Tomorrow's temperature T is belong to 60 to 85, and I define x equal to 1 if T larger than 80, include 80, and x equal to 0 if T smaller than 80. then x is a random variable, right? And the PMF, I don't know the probability. I suppose this one, probability t smaller than 80 has like a 80%, right? Suppose we have these. Then the PMF will be x can have value 0 and 1, and the probability will be smaller than 80, that is 0. This one's 0.8 probability, right? And this is 1. According to this one, the probability will be another side, right? It's 0.2. So we have Px of x equal to 0.8 if x equal to 0, equal to 0.2 if x equal to 1, and 0 otherwise. Right? So this is Px. Right? And then CDF will be f capital X of x equal to the probability of capital X smaller than or equal to the lowercase x. So its value you need to check this. So we have two values, right? 0 according to 0.8, 1 according to 0.2, and all the others are zeros. And here's a smaller than. So for 0, just for x smaller than 0, it will be 0, right? Similar with this case. X smaller than 0, then no capital X can be here. So you always cannot have this. Similar here. You can never get the result so that capital X smaller than x. Here the capital X is random variable. It depends on your experiment. It's a result of the experiment, right? You measure some value from the result of the experiment. And this lowercase x is a value in the random variable, value of the variable. So if this x is smaller than 0, then capital X, because you can only have 0 and 1. So impossible. This is a probability 0. And similar, if x is a value between 0 and 1, then capital X can be 0, right? Capital X can be 0. Capital X is 0 according to probability is 0.2. And then we consider 1 x larger than 1, right? Larger than 1. X larger than or equal to 1. Then this, according to capital X, can be 0 or 1, right? Can be 0 or 1. This is a no capital X. And this capital X can be 0. And this, the last one, capital X can be 0 and 1. 0 or 1. So 0 and 1, right? Do summation, it is 1. So this is CDF. And as a graph, this graph for PMF, we have here's a 0.8 and here's a 0.2. This is X, this is a PMF. And this one, similar with this, right? Some steers. So 0.2 here, then this is 1 here, and we have a solid circle, and here's a empty circle. So here means here means the value is here. When x equal to 1, the function's value is this one. not this one. Alright, so it means this bar we're close to 1 but never go to this point. Okay. And this 0 is also same thing. So here's a bar. When x equal to 0 and 1, the values are 0.2 and 1. Okay. So this is a CDF, PMF and CDF. Alright. Okay. Let's check. Let's give. Actually, here we have 2 cases of this kind of thing, right? This coin sample and temperature sample, and then generally we can have another. We can have a definition we call Bernoulli distribution. Bernoulli distribution of Bernoulli distribution. That means we have a random variable x. Its value will be 0 or 1, and the probability probability. Am I good? Probability. Use this one for some p. Here, this one is some. That will be 1 minus p. 1 minus p. P will be a value between 0 and 1. 0 and 1. If you want, you can also like p equal to 1, for example. That means only the x can only have value 1. You can also think, okay, the p might be 0. P might be 0. That means capital X can only have 0. Okay. And then you have the mass function, probability mass function. It is a px of x or equal to. It is p if x equal to 1. It is 1 minus p if x is 0. It's 0 if x do not equal to 1, do not equal to 0. For all the others, right? For all the others, this PMF. It looks like here's a p, here's 1 minus p. This is 1, this is x. Right? And the CDF, it is a f x of x or equal to. Okay, this is the probability of capital X smaller than lowercase x, right? This is this one. Okay, you can check. Now capital X can only be 0 and 1. So if x is a negative value, impossible. The probability is 0, right? No x here. No x here. No x satisfied. It's smaller than, even smaller than x. And if x is a value between 0 and 1 but not include 1, then x can be 0, right? Can be 0. 0 is smaller than this x. So here's 0 is a probability of 1 minus p. And if x is a value larger than or equal to 1, so x can be 0 or 1. Then the probability is 1. Probability is 1. We can have a graph. It looks like 0. If x is smaller than 0, x is negative, the CDF value is 0. And when x between 0 to 1, this value is 1 minus p, right? 1 minus p. And when x is larger than 1, the value will be 1. Yeah, this is CDF. So we call these as Bernoulli distribution. This use a lot in a lot of places, because the things like that. You have some experiment. Like here, we want to know the temperature of tomorrow. Then you can define the event. This is an event. This is an event like A. And this one is an event AC, right? A and A complement. A, we have a probability. I think I gave a probability, right? I said this is a probability. A is like a point A, and AC will be probability, will be reverse way, right? So it's 1 minus that is a 0.2. The rest of the A, right? Inverse of the A, yeah, complement of the A. So this is 0.2. So if this is a P, this will be 1 minus P. Alright. Then you can have this Bernoulli distribution, and we denote this as a Bernoulli P. Right? This is P. One has probability P. So Bernoulli P. So any experiment, you consider the event of that experiment as 1, and you consider the complement of that event as 0. You can have a Bernoulli distribution. So any experiment, you can have a Bernoulli distribution. So we use this a lot. Bernoulli distribution. Okay. Now we can consider another one. We consider like okay, this is a binomial distribution, and we denote it as binomial NP. That is what? Suppose we have x1 to xn. All of them obey. I use this one means obey Bernoulli P. So each one is a Bernoulli. Each one has Bernoulli distribution. Suppose we have random variables x1 to xn. Each one obeying a Bernoulli distribution and independent each other. They are independent. Now let x equal to x1 plus xn. Okay, we say x obey Bernoulli distribution, binomial distribution. The binomial distribution, right? It's a summation of n Bernoulli distributions. Yeah. Okay. Then what it is? I want to have a look. We know each xi, so a values of x. So each xi has value 0 or 1. So x1 plus xn, the value will be between 0 until n, right? All of them are 0, you get 0. All of them are 1, you get n. Some 1, some 0, you get the value between 0 and n. So its value of x will be a value between 0 to n. 0 to n, right? So 0 to n. And the probability. Probability of x equal to k. What it is? equal to k, that means k of xi's are 1, right? And n minus k of xi's, they are 0, right? So this probability or equal to, okay, we have n, we choose k of them, they are 1, and 1 has a probability p, right? It's Bernoulli p. So 1 has a probability p and k of them. We just studied the counting problem, right? Counting problem. Yeah. And another n minus k, they are zeros. 0 has probably 1 minus p and n minus k of them. Okay, so we have this one. We have this one. And the k will run from 0, 1, 2 until n. So this is the probability of the binomial distribution. And actually what it is, this is a mass function, right? Mass function, PMF. It is a P capital X of X equal to the probability. This is a definition, right? Here's a definition. And then we use a counting method. We know this probability. Okay. All right. Then what is CDF? There will be you need to do a lot of calculations. So usually people do not give the CDF of this one. We just give the PMF. There will be fine. We can have a looking at a graph. This n will equal to 0, 1 until n, right? 1 and 2, and here's n minus 1, things like that. When it is 0, when k is 0, then this is choose 0 from n. Actually, this is 1. See 1, choose 0 from n. This is 1. And the p to the k is 0, so this is also 1. And now it's 1 minus p to the power n, k0, right? k0. So this one will be a value like this is 1 minus p to the n's. And the other side, if k is n, choose n from n, this is also 1. And the p to the n, so we have p to the n, and this will be 1 minus p to 0, because k is n, right? n minus k is 0, the power is 0, so this is 1 minus p to 0, this is 1. So the last term is p to the n, and then other values were between them. Actually it will look like this. It looks like this. Yeah, depends how many, what is the n, right? Something will look like this. If you want, you can use a computer, you use a MATLAB, you can try, you choose different p, you can see these values. So how it looks like. Maybe it looks like this, or maybe it looks like this. This side is a p small than 1 minus p, and in this case is a p larger than 1 minus p. Okay. Yeah, if p larger, this side is large. If 1 minus p larger, then this side is large. Yeah, something like this. And if they are equal, they will be like a symmetrically like this. All right. This is a binomial distribution. Okay, that's all for today. See you next time.